Welcome to our channel. Let's have a look at the problem 1522, number of subarrays with odd sum. So in this video, we are going to solve it using dynamic programming. So our plan is the following. So first, write a solution with O of n space, and then improve it to a solution with O1 space. So solving the problem is not our purpose. So demonstrating the progress from On to O1 space is our purpose. So this is the one thing. Afterwards, we'll also make some comment on some extensions or variants of the problem. So with that said, we are ready to look at the problem statement. So here we are given an integer array, and we want to return the number of subarrays with an odd sum. So we need to return this modulo sum big prime, that is 10 to the power 9 plus 7. So here, if you look at example 1, actually it lists all the subarrays valid. So the answer is going to be 4. So here the array length is bounded above by 10 to the power 5. So this is a decent large number. Therefore, we need to think of time complexity. So here the array, the integer is in between 1 and 100. This is not very essential. So with that said, we are ready to do the coding. So here, actually, when you use dynamic programming for solving problems, so here I'm using tabulation. So the interpretation will be very important. So I'm going to interpret like this. So first introduce this length. This is just for convenience. So array. So odd is going to be 0 times n, and even will also be 0 times n. So we initialize two arrays, both of length n. So here the odd I, meaning that the number of valid subarrays ending at index I, right? So here, using this interpretation is very easy to do the coding. So you can also interpret, say, odd I is the number of valid subarrays up to index I, but can ending at any previous indices. So this is just a individual and some differences. But here I'm using this one, number of valid subarray ending at index I. In other words, the array should end at index I. So afterwards, we just need to do the sum and then modulo this prime number. So that's our main strategy. So here, actually, the even also comes into play, because odd number plus even sum still get odd number. And odd plus odd, you are going to get odd. You are going to even, right? So then let's write here. So odd plus even yield odd, right? Odd plus odd yields even, and even plus even also yield even. That's trivial, right? So now here even can be interpreted the same, right? The number of valid subarrays with odd sum valid subarray. So let's see, with odd sum ending at index I. So similarly, let me write here, maybe just for clarity, right? So even I is number of valid subarrays with even sum. So number of valid subarrays with even sum. So so our at the index I, right? Ending at the index I. So what we want to return finally will be summation of odd. So modulo this big constant 10 to the power 9 plus 7. So this number actually is a prime number. You can check that. So now let's look at the DP update rule, right? So here, in order to do this, first, if array 0, so modulo 2, let's see, if it's 0, so this will be an even number. So I'm going to set even 0 to be 1. Otherwise, it's an odd number. I'm going to set odd to be 1. That's it, right? So this is the first one. So now we are going to iterate. So for I in range 1 up to n minus 1, right? So still we are going to check if if array I modulo 2 is 0, that is even, right? So if it were even, right, so then even I, so it can be this number itself, right? We just this is the ending at index I, or any previous number ending at index I, any subarray ending at index I minus 1 as has an odd even sum, then add this even number still even. So this is the even. For odd I, because the current number is even, you cannot count this number. But any subarray ending at index I minus 1 with an odd number, then plus this number array I will be an odd subarray, right, sum. So that's the odd if the number array I is even. So then if otherwise, so it will be odd, right? Then odd I will be, first you can count this number itself, and then you can count any subarrays ending at index I minus 1 but with an even sum, because even plus odd, you're going to get odd. So how about even I? So because this number currently is odd, you cannot count this number itself, but all the odd subarrays ending at index I minus 1 plus this plus this odd number, so odd plus odd, you are going to get even. So that's it, right? So this way we set the DP table. Then afterwards we just need to do the return. Let me first run it and then submit it. Yeah, it passes all the cases. So now what I'm going to do is to print out this odd and even so that you can have a better understanding. So print out odd. Let me do this. So then I'm going to print out, so this even, right? So let's see. You can try to interpret this one. So the number odd ending at index 0 is 1, even is 0. So here the number of odd ending at this 3 is also 1, just 3 itself. You cannot include 1 because 1 plus 3 is 4, even. So here at index 5, at index 2, so you get 5 itself. Then you can 5 plus 3 plus 1. So 9 plus 4 plus 5 is 9, is odd. So similar, you can see even. So any at 1 is 0. Any at 3, 1, because you can count 1, 3. Any at 5 is also 1, because you can count 3 and 5. Then this odd adds together, so you're going to get 4. So this is one solution. In this solution, the space-time complexity is for sure space-time complexity will be O of n, right? And the space-time complexity is also O of n due to the initialization of this odd and even. So what we want to do next is to improve this format of solution to be O1 in space. Let me copy this part. And also I'm going to comment this part, because if you use print to then submit, you might have output limited problem. So now I want to use this to be O1, right? So what we do, actually, we just trace this odd and even. So we do this using two variables. So odd previous and even previous. So we can set it to be 0 and 0, right? And also we have a result variable. So each time we are going to add the odd, right? So here let's iterate for I, y in enumerate. So array. So if y modulo 2 is 0, that is even, right? So if it were even, so I still do interpretation of odd and even to be the same as odd I and even I, right? So here, so let's look at the odd, because it's even, so the even null, first we can count the number itself, and then we can count the previous even, so even previous. That's one thing. And also let's look at the odd now. Because this current number is even, you cannot count this number itself. But if the previous one is odd, then you get this this even number. So you are going to get odd. So we can odd now actually is odd previous, right? This is the one. Another one is if current number is odd. So because it's odd, so I can first count itself. Let's see, odd now equals 1. So odd plus even will be odd. So we can consider the even previous. So even previous. This is for odd now. So for even now, because the current number is odd, we cannot do 1. But if the odd previous, right, this is the number, then plus the odd number now, you're going to get even. So now you can update even now to here. So this actually, this if and else is corresponding to this if and else in the exact fashion. But the difference is that I absorb the 0, the first element in here into this for loop. So then each time I'm going to do result add this odd now, right? The first initialization we don't need to add because it's you can think of it just some dummy one. So now after this you are going to do odd previous and even previous to be odd now and even now, right? So finally you just do the return. You do so here the result actually is corresponding to the sum, right? So it's just the result. So let me first try to run it. So solution has no attribute. Yeah, I guess that's what's the problem. So here I need to do some indentation. So put it here. Yeah, it passes the 3 test cases. Now let's look at the generic case. Yeah, it passes all the cases. And obviously, for this version of solution, so the space complexity is 01, slightly improved. With that said, I guess the coding part for this problem is done. So now, let me make 2 remarks. First is you need to pay attention to the ON to O1 process in improving the space complexity. This is the one. Another one is some extension, right? So here I'm considering the number of subarrays with an odd sum. So symmetrically, you can consider even sum, right? Actually, the nature of the problem does not change. So what you want to return actually is sum here changed to be even. And in this result, each time you accumulate even now, right? So that's the one extension. And another one is that here let me write like this. So here we consider subarrays. In other words, consecutive pieces. So how about subsequences? Yeah. Can you try to solve the second problem? That's also a good practice, I guess. So with that said, I guess that's it for the current video. Thank you for